All right, we're going to take a look at another type of differential equation. It's called a Cauchy Euler equation. So it just has a slightly different form than what we've seen in the past. Now, here's the generic form, and of course it looks ugly when it's written like this, but the big idea for what the Cauchy Euler form is for every derivative, there's a multiple of x out front that the power on the x matches the derivative. So a quick little example of this might be x squared y double prime minus 5xy prime plus 6y is equal to 0. All right, notice that the power on the x matches the derivative that it's paired with. Right here, no derivatives, so no powers of x. All right, this is what's called Cauchy Euler form, and it can go up to ever high derivative as you want, as long as the power matches that derivative. To solve an equation like this, we're going to do a lot like we did with our constant coefficients. We're going to guess at what type of solution we should expect. Well, think about it. Whatever our answer is, if we don't take any derivatives, it should be the same type of function if we take one derivative and multiply by x, or take two derivatives and multiply by x squared. Now, since we're multiplying by a power of x, that means it's going to increase the power of any x that's there. So think about it. If we assume that our solution will be x to the m, right, just the power of x, that should work, right? Because whatever derivative we do by bringing down the power, the multiple of x will bring it back up to the original power. So that means they would all be like terms, and this should work. So the same idea, all we'd have to do is take all the derivatives, plug it in, and see how it works. Now, just like before, we need to see how to represent our solutions. So let's take a look at now, just like before when we were dealing with constant coefficients, once we take all the derivatives and plug it into this differential equation, we're going to end up with a characteristic equation, which is just going to be a polynomial equation, just like before. So we're going to have different types of solutions. If we have distinct real solutions, that just means if it's a second order differential equation, you get two different real numbers out of it. Your answer is going to be very simple. Let's say we got M1 and M2. We get distinct real solutions like this. Then your solution would be x to the M1 plus C2 x to the M2. And if it was, you had three solutions, four solutions, it would just continue along like that. The second one, what if we have repeated real solutions? Well, for repeated real solutions, when we were dealing with constant coefficients, we multiplied by an x, right, for each time it was repeated. Well, it's going to be slightly different here because we already have a power of x. You can plug it into our formula from before, but let's say we have M1 equals M2, right? We have the same solution. Well, instead of multiplying by x here, what ends up happening, our first solution, of course, is going to be M1. Our second solution, we multiply by the natural log of x, right? Because that's this is just x here. We already have x, not an exponential, so kind of think about it as the opposite of an exponential would be a logarithm. Now, of course, if it's repeated again, so on and so forth, so if it was M3, so just like before, we'd have C3 x to the M1 natural log of x squared, and then cubed, and so on and so forth. Now be careful. The natural log of x squared is not the same thing as the natural log of x squared. Those aren't the two things, so you gotta make sure that you have the entire natural log in the parentheses. Now, if we have one more case, complex conjugate solutions. So kind of like our M1 is alpha plus I beta, and M2 would be alpha minus I beta. Now, when we had constant coefficients, we used Euler's identity to get to an exponential and sines and cosines. We can still use that trick because, I'm just going to scribble this out real quick. Our first solution would be x to the alpha plus I beta, something like that. Well, again, we can break this apart as x to the alpha, because remember, alpha is just a real number, x to the I beta. So again, it's that I beta part that's a little bit tricky. Now, here's the way we can do it. Watch. I can rewrite x to the I beta as e to the natural log of x, right? That's just x raised to the I beta. Power raised to a power there, you can multiply, so this is e to the I beta ln x. And using Euler's identity, remember e to the I theta is cosine theta plus I sine theta, then I can rewrite this e to the I beta natural log of x as cosine beta ln x plus I sine beta ln x. Right, so instead of just a theta, we have a beta ln x. That's a horrible beta. Okay, so you can see it works out almost exactly the same. So let's go back up here and just translate this into what we would expect. We saw constant coefficients. Our solution looks something like this. X to the alpha, and then we'd have, I forgot my C1. C1 cosine beta ln x plus C2 sine beta ln x. Okay, so there are the three forms of our solutions. If they're distinct solutions, then it's just x raised to that power. If it's repeated solutions, instead of multiplying by x, we multiply by the natural log of x. And if you have complex conjugates, you get a real part, and then a sine and cosine that comes from the I beta part. So it's quite a bit like what we've seen before with constant coefficients, just we have to modify just a little bit. So let's just take a look at a few of these. Just say our directions here were solved. So let's say we got x squared y double prime minus y prime minus 15y is equal to 0. All right, so first, I forgot an x. First thing we'd want to do is you need to classify this. So this is a second order linear differential equation, non-constant coefficients, but it does have the form for a Cauchy Euler equation. The power on the x exactly matches the derivative. So we know to do this, we're going to assume y is equal x to the m. Now, when we're dealing with constant coefficients, it was pretty easy to jump straight from this assumption to our characteristic equation. It's not quite that easy anymore, so you're probably going to want to do this step for a while. So let's take all of our derivatives by double prime, it's m minus 1, x to the m minus 2, and plug it into our differential equation. So I have x squared times m minus 1, x to the m minus 2, minus x times m x to the m minus 1, minus 15 x to the m is equal to 0. Now once you plug in your solution, go ahead and multiply this stuff together you can. You should be able to multiply x's here. So I have m minus 1 x to the m minus m x to the m minus 15 x to the m equals 0. Now if every term doesn't have that x to the m in it, you've made a mistake somewhere, either in your derivative, your multiplication, or it's really not a Cauchy Euler equation. So now since everything has an x to the m, I can factor this out. And I got m minus 1 minus m minus 15 equals 0. Now we could technically divide out that, that x, because the only way x to the m is equal to 0 is if x itself is 0. But if x is 0, that means that y has to be 0. That's the trivial solution, and we're not interested in that. So at this stage, you can either factor it out or divide it out, but you're going to end up with m squared minus m minus 15 equals 0. We end up with a characteristic equation, which is m squared minus 2m minus 15 is equal to 0. That'll factor, right? That's m minus 5, m plus 3 is equal to 0. So skipping a step here, we get two distinct solutions for our characteristic equation, two distinct real solutions. So our solution to this is c1x to the 5th plus c2x to the negative 3. And you're done. Now if you have any initial conditions, now is when you would apply the initial conditions to figure out what C1 and C2 are. So it works almost exactly the same way, except for the characteristic equation ends up being slightly different when you do it like that. Let's try another one here before we take a look at the non-homogeneous case. Let's do it a little bit harder. Let's say if I have x to the third y triple prime plus 5x squared y double prime plus 7xy prime plus 8y equals 0. Okay, this is a third order linear differential equation. These are not constant coefficients because we have x's there, but the power on the x exactly matches the derivative. Third power, third derivative. Second power, second derivative. First power, first derivative. No power, no derivative. So this should work. So we should be able to assume y is equal to x to the m. Now we're going to take all of our derivatives here, and again, you're going to want to write this out. Y double prime is m minus 1, x to the m minus 2, and y triple prime, m minus 1, m minus 2, x to the m minus 3. All right, once we plug this in, this is going to be kind of messy. We get x cubed, m minus 1, m minus 2, x to the m minus 3, 5x squared, m minus 1, 7x times m, x to the m minus 1, plus 8x to the m equals 0. All right, so big mess. Now notice, oops, I forgot my m minus 2 here. Squeeze that in there. Okay, so once we multiply all the x stuff together, we should end up with an x to the m in each one of these. X to the m, squared m minus 2, so that gives me 5m, m minus 1, x to the m, 7 m, x to the m, plus 8x to the m equals 0. All right, so looking at that, everything has an x to the m. So I can either divide it out, because again, if x is equal to 0, that means y is 0. That's a trivial solution. Or we can factor it out. This time I'm going to go ahead and just divide it out. So I have m minus 1, m minus 2, 5m, m minus 1, 7m plus 8 is equal to 0. I probably have to come way over here. All right, so that's a polynomial equation in m. So I guess we should just start multiplying everything out. So I'm going to kind of cheat here just a little bit before I move over here. I know if I multiply this out, that's going to be m squared minus 3m plus 2. So when I bring that up over here and we multiply it out, I'm going to multiply that by m. So that's m cubed minus 3m squared plus 2m. If I distribute that 5m, that's plus 5m squared minus 5m plus 7m plus 8 equals 0. All right, I can combine some like terms here, so I get m cubed plus 2m squared. So that plus 4m plus 8. All right, we have a third degree polynomial to solve here. So we're going to try factoring first. If factoring doesn't work, you have to do something like synthetic division. I believe this factors what I'm looking at, right? If we factor by grouping, out of the first pair I can take out an m squared, and I'm left with m plus 2. Out of the second I can pull out a 4, and I'm left with m plus 2. Yeah, that'll work now because we have two terms and they both have an m plus 2. Left with m squared plus 4. All right, so either this is m plus 2 is equal to 0 or m squared plus 4 is equal to 0. So either we have m is negative 2 or m is equal to plus or minus 2i. Kind of skipped a step there. Okay, so we should be able to write down our answers now. Because what do we have? We have a real part. So for this, that would be c1 x to the negative 2 plus. Now here we have a complex solution, which means we get what exponentials and sines and cosines stuff. Since the real part's 0, we would write this like this. this would be x to the 0. I know I got C1 over there, but C1 cosine beta ln x plus C2 sine beta ln x. Right, so that's fitting into here exactly, right? There's our alpha and beta is 2. Now I'm just going to change my number since I already have a C1. This is going to be C2, since x to the 0 is 1, I'm just going to say this is cosine 2 ln x plus C3 sine 2 ln x. Okay, that was a third order differential equation. Oh, it's way over here. So we were expecting 3 linearly independent solutions, and there they go. All right, so you see it works quite a bit like our constant coefficients. We've just modified it slightly. Now the other place that you might, this needs to be modified is if we have a non-homogeneous differential equation. So I'm actually going to go way back over here so we have plenty of room. All right, so let's say I have x squared y double prime minus 3xy prime plus 3y is equal to x to the 4th e to the x. Okay, again, this is a second order linear differential equation, non-constant coefficients, but it does have that Cauchy Euler form. Now in this case, this happens to be non-homogeneous. The good news is our approach strategy is the same. We want to go after the homogeneous first. So we're going to look at x squared y double prime minus 3xy prime plus 3y is equal to 0. Assume y equals x to the m and plug it in. Now, you really want to make sure you're writing this out. I am going to skip a step here. This is going to be m minus 1, x to the m minus 2, minus 3x m x to the m minus 1, plus 3x to the m is equal to 0. Again, just kind of skipping a quick step here. Now, so we get m minus 1, x to the m, minus 3m x to the m plus 3x to the m is equal to 0. We can factor that out, and I'm going to distribute here a little bit. We get m squared minus m minus 3m plus 3, or m squared minus 4m plus 3 is equal to 0. I'm out of room down here, so let's go ahead and find our homogeneous solution. That's our characteristic equation. That should factor to m minus 1, m minus 3 is equal to 0. So we get two distinct real values for this. So our complementary solution, C1 x to the first plus C2 x to the third. Okay, so there's our homogeneous solution. Now that we've solved the homogeneous, kind of like the way we always did, now we go after the non-homogeneous. So this is a piece that's the non-homogeneous. Now, when you're looking at this, you would say, okay, that has a repetitive derivative. I could use undetermined coefficients for this. The problem with this is, and this is why I would suggest always using variation of parameters with Cauchy Euler equations, is you almost always forget, for that to be the function to do undetermined coefficients, you need to divide through by x squared. And you need to do that for variation of parameters anyway. So if we divide through, kind of combine two later. For the non-homogeneous, I'm going to go ahead and divide through so we see what our function is, minus 3 over x y prime plus 3 over x squared y is equal to x squared e to the x. All right, I would suggest here, and it's a pretty good suggestion, use variation of parameters. Now remember how we do variation of parameters, we got to come up with three values. We got to come up with what w is, w sub u1 prime and w sub u2 prime. All right, w is just our y1 and y2 from the homogeneous, and then its derivatives, 1 and 3x squared. We do that determinant, I get 3x cubed minus x cubed, which is 2x cubed. All right, for this, for w sub u1, I'm going to replace the first column was 0 and x squared e to the x. Then I get x cubed 3x squared. So what we do, we multiply down the main diagonal, that's 0 minus, down this diagonal, I get x to the 5th e to the x. X in 1, it gives me 0x squared e to the x. So for the second one, I replaced the second column with 0 and our function. Multiply down the main diagonal, so I get x cubed e to the x minus 0. Okay, so the two values that we need, I'm going to write it over here, then we're going to go way back over there. So mu1 prime is equal to w sub mu1 prime divided by w. So this negative x to the 5th e to the x divided by 2x squared. mu2 prime, w sub mu2 prime, come on, divided by w. So it's going to be x cubed e to the x divided by 2x squared. All right, hold on, I gotta grab a pen. All right, so now to find mu1 and mu2, all we have to do is integrate those. So u1 is equal to the integral, well, that's 1/2 out front. What do we end up with there? Negative, so let's go ahead and pull the negative out front too. Negative x to the 3rd e to the x. And u2 is going to be equal to, well, again, that one has a half, so let's go ahead and pull that out front. And that's just going to be x e to the x. All right, for this one, this actually, I'm going to squeeze it right here. Okay. This type of integral works out very well by using by parts, but you can use what's called the tabular method for this. Let's take a quick look at this if you haven't seen it before. We're going to make a table here. The first one's going to be a sign. The next one's going to be a derivative column, and then we're going to have an integrate column. The sign column always starts with plus and then alternates its way down. And we don't know how many we have to do yet, so just do a couple. So let's take a look at this. We're going to start with which function would we take the derivative of if we were doing by parts? That would be x cubed. The function that we would integrate would be e to the x. So in this column, start taking derivatives till you get down to 0. 6x, 6, and 0. Okay, the other one, integrate till you get down to the 0 row. Now the good news is the integral of e to the x is just e to the x, so that works out really well. Notice I went down to where it was 0. Now all we got to do actually is just read off this answer. It's this easy. You move across the first two and then down at an angle. So the first term when we do by parts is going to give me x cubed e to the x. By the way, there's a negative 1/2 out front there that I haven't done. Yeah. Then the next one is going to be minus, let me just move that over just a bit. I'm going to write that negative 1/2 x cubed e to the x minus 3x squared e to the x. Then moving across down, it's going to be 6x e to the x. Over that in a second. Minus 6 e to the x. Now notice, everything after that would be zeros because this column is all zeros now. So that's that first integral. You're done. That's how quick and easy that tabular method is. So we can do the same thing for this one, since the table is going to be much, much quicker to do. We have a sign, derivative, and we're going to integrate. Plus, minus, plus. We're going to take the derivative of x, and we're going to integrate e to the x, e to the x, e to the x, and then just move across and down. So the first one's going to be x e to the x minus e to the x. So this is going to be x e to the x minus e to the x. All right, now here's the good news. We're basically done, right? We found mu1 and mu2, so we know our particular solution is mu1 y1 plus mu2 y2. So our particular solution, mu1's all of this mess, so I'm just going to go ahead and write it as the same thing. X cubed e to the x, 3x squared e to the x, 6x e to the x, 6 e to the x, times y1. Well, our y1, if I remember right, was just x, plus mu2, x e to the x minus e to the x, times our y2. And our y2 was what? X to the, what was our y2? Squared? Cubed. Check that, I can't remember what that was. What was y2? It was on the board a second ago and I can't see it on the board anymore. Was x cubed? I'm going with x squared. I'm sticking with x squared. Okay, so there's our particular solution, so I'm not going to write it all out. So our entire solution, y is equal to yc plus yp. So our particular solution, we already had on the board, our complementary solution, that's your particular solution. So in problems like this, you can see how helpful using this tabular method for integration is going to be. So we have a brand new type of equation that we need to recognize. It's called a Cauchy Euler equation. It's where the power of an x out front matches the derivative. If you see that, use the assumed solution of x to the m, plug it in, find your characteristic equation, and then the non-homogeneous part is going to work like it did in the past, but I highly suggest using variation of parameters.